In this video, we're going to be looking at parabolas. Now, parabolas are defined as a set of points in a plane that are equidistant from a fixed point f, which is called the focus, and a fixed line called the directrix. So let's go ahead and draw a graph of a parabola. So let's say this is the x and the y, and the shape of a parabola is like this. And we will see we have, I'll use a different color for that. We have a line here and a point here. And all the points, like such as, let's say, this point and this distance, the distance from this point to that particular point and from the red line to that particular point is equal. Similarly, if we just choose another particular point, such as, let's say, this point, the distance from the line here and from the point here is equal. And you can do it for any other point. They will always be equal. That's how a parabola is defined. So let's say this is this is the point, right? So this is f, the focus, and let's say its coordinate here is a constant p, comma 0. So if this is the origin of the graph here, the distance here is p. Now one thing to note is the distance of this line from the graph is also p. So it's like equal distance from the center to this line, which we call the directrix, and from the center to the focus as well. So as I discussed a while back, if we choose a point here and look at its distance from the line here, so this line extends all the way up. Let's geometrically label these points. So let's say this particular point here is let's say A, and let's say its coordinate is xy, and let's say this point, the distance again, so this point, let's say, is m, and its coordinate, as you can see, it's negative p on the x-axis, and let's say y on the y-axis, as it's the same height compared to A. Let's say the origin is O here, and this is Z. So OZ is equal to OF. Now, if we want a quick derivation of this, we can basically say that the length of FA is equal to the length of AM. So let's think of the distance between these points. You can calculate the distance between these points as x minus p squared plus y squared, right? Y minus 0 squared is equal to this distance, which is x plus p squared, x minus p squared, plus y minus y, which is 0. So we just have x plus p squared. If we square both sides, we would come up with this, and you can simplify this right away. You can simplify this right away to get the equation y squared is equal to 4px. Now, if you remember from the last video, this was the standard form of a parabola centered at the origin. Now we can definitely have the parabola shifted, and in that case, if the y coordinate is k, we would have, and the x coordinate is h, we would have an equation that looks like this. And that is again another standard form. It's the same thing. So what we'll be doing is we'll be using this equation as a base, as a reference to construct all of the equations and the points we'll look at. So the equation for the equation of the parabola, where we have y squared is equal to 4px, we will define a particular few quantities which you already saw from this graph. So let's go ahead and write them. So the turning point, or an extreme point here, the O, is called the vertex. So in our geometrical diagram, we would say the vertex O is equal to here 0, 0. We then have the focus. If you remember that fixed point, the focus here is F, which has the coordinate p comma 0. And then the fixed line here is this mz line, right? So it does stretch beyond z, but for geometrical purposes, I'll just write mz. Equation of the directrix. Equation of directrix here in our geometrical diagram, mz, is this. It is x plus p is equal to 0. Or you could write x is equal to negative p. I hope that's clear because you can see that the x coordinate here for this diagram is just a negative p. It's a line there. So that's the equation for the directrix. We can also talk about an axis of symmetry. So let's see what that is. The axis of symmetry is a line that divides the parabola to equal symmetric parts, as you can see the top and the bottom here. So this line, as you can see here, is y equals 0, right? So the axis of symmetry here, all right, equation of axis of symmetry here is, we have just a y equals 0. We can also define another quantity, which I have not shown in this diagram, so I'll go ahead and just plot that down in purple. So let's say we have a line here right across the focus that meets these 2 points. So let's label these points L and L prime. This line is called the latus rectum. Latus rectum. It's a line that goes through the focus and cuts the parabola at points L and L prime. Now this part, this length here, is just a 2p, and this length here is also just a 2p. So you can see that the length of L to L prime is a 4p. Now that might vary since we will be using a notation for p, so p can be negative or positive in our discussion. So let's go ahead and write that down. Let's first write equation of latus rectum. So what's the equation of latus rectum? The equation here is x is equal to p. As you can see, if I just wanted to write down an equation of this line, it goes through p, and so it's x is equals p. Now the length of latus rectum is just absolute value. So I'll just write LL prime is equal to the absolute value of 4p. In our convention, in my videos, I'll be using I'll be considering p can be negative or positive, and so you will have a value given for that. So these are the quantities we'll be using for identifying parts of a parabola. Now let's go ahead and see what I mean by having a negative value of p. So if we do have a negative value of p, this is how the graph would look like. It would be opening on the other side. So if p was negative, this should pass through the origin, and yeah, I just redrew that. So you can see that this would mean p is less than 0. Okay. And in this case, we have p is greater than 0. So it opens to the right when it's greater than 0, opens to the left when it's less than 0. This is a convention I'll be following. In some textbooks, of course, you'll find y squared is equal to negative 4px. So they take this constant to be always positive, but I'll be not using that. So we have seen the left and the right opening, right side focused um, parabola, but let's go ahead and see what would have happened if we had a parabola of this form or of this form. So as you can predict, this would have p is greater than 0 and this would have p is less than 0, but our equations would be a bit different. So the vertex here would still have the same structure, x and y. So I'll show a couple of examples on that. So the x would have the value h and the y would have the value k. So that's the vertex here. The fixed point here is going to be 0, p. The directrix, as I've geometrically shown, is going to have the equation y plus a is y plus p. Y plus p is equal to 0. And the axis of symmetry, I'll just write axis of symmetry, is x is equal to 0. And the latest rectum, the length of the latest rectum is still 4p. So the differences that came up, as you can see here, the x is just shifted with the y, it's replaced with a y. The focus points have changed. It's p comma 0, so it was ahead on the x-axis by p here, but here the focus is here. It's 0 comma p. It's rising on the y-axis, and the directrix is going to be a line like this. So so this should be like y is equal to negative p, right? And if p is less than 0, I believe you understand that the focus is here, the point is there, and that would kind of follow through. If I place the value of p as a negative number, for example, negative 1, 0 comma negative 1, this would make sense, right? 0 comma a negative 1, the value of p being negative. And the directrix again, y is equal to negative p. Now if I have a negative number, that would become as a positive number, right? So y equals 1. So that's the directrix. So this is how we have categorized all of the parabolic shapes. So we would have to keep these in mind to go ahead and solve problems. So these are the cases for the equation with the with the form of this 4py. So the squared is on the x, and we will use these values, these points and equations. In the next video, we'll be looking at a couple of examples, a couple of example problems for parabolas.